Analytical and environmental chemistry mark our first excursions into lab where we have a lot more independence. We'll be working with a much wider variety of molecules than we have in other labs, and while our priority is always to use the safest procedures possible, there are a wider range of risks that we'll encounter. On primary containers, those that we'll get our original materials from, these risks are often indicated with the GHS, or Globally Harmonized System. The symbols of the GHS, which you can see on the left, are meant to give a very visible indicator of what you should keep in mind when using a reagent, or storing it, or disposing of its waste. The most common hazard label is a flame, which you can see in the top left. The flame is an indicator of the inflammability of a substance, how easily it can be lit on fire. Most organic reagents are going to have high flame ratings and therefore carry this mark. The next symbol is a flame over a circle, which indicates an oxidizer. This means that it can remove electrons from other molecules, and so we generally want to keep oxidizers separate from anything that can easily be oxidized. Organic molecules, again, being a good example of something that could be easily oxidized. So these oxidizers should not be stored near the inflammable substances. This hazard label on the top right is an exploding bomb, indicating something is unstable or self-reactive. Generally, I avoid these even in the advanced labs. These need particularly special care. Although on a side note, one of our graduates works to test chemical hazards like flammability and temperature stability. So it's not to say that we don't prepare you for this type of special handling. In the second row, we have a corrosive indicator, which is a picture of a substance dissolving the table or a person. These are often strong acids or bases, which we'll use in lab. So this is something that you'll see. Gas cylinders are reserved for cylinder gases. We have a few of these in lab, argon tanks for our microwave plasma instrument, and helium for our gas chromatograph mass spectrophotometer, a GCMS. These are always going to be strapped for safety, so you shouldn't need to worry about these, but there are special handling instructions for cylinders. The skull and crossbones hazard indicates booty attractive to pirates like gold or silver, or possibly acute toxicity like a poison. You get to guess which one. In the bottom row, there's an exclamation mark, used to indicate a lower level of risk than corrosion or skull and crossbones, or the health hazard, which we can see in the bottom right. So it's indicating there's some sort of hazard, but it's not quite as bad as corrosion, skull and crossbones, or the health hazard. The health hazard is for things that won't kill you outright. They'll just destroy an organ or give you cancer. And our final hazard symbol in the bottom center is an environmental hazard symbol. This designates how we should deal with our waste. This symbol indicates how that if we flush this down the drain, all of the fish and trees will die. As the fish die, they will also begin to look more like goldfish crackers than real fish, creating a secondary hazard. We don't want that, so we'll take proper care of our waste. These labels may sound scary, but the risks are most significant if they're not controlled. We can use flammable substances in fume hoods and keep our hair tied back near flames. We're going to store oxidizers properly and use gloves when using corrosives. We're going to keep all food and drink out of lab and wash our hands before we leave to dramatically reduce risk. In addition to these, we're always going to be wearing goggles, clothing that covers our legs, and just in general, keeping long hair tied back out of our way. And most of the time, we won't eat our reagents. Hazard information is found for any individual molecule using the MSDS, which stands for Material Safety Data Sheet. You can find all of them digitally through TrollWeb. Navigate to the physical plant portion under Departments, and then the MSDS online service is the only thing that has an awesome icon. It is, after all, a velocity EHS solution. Try clicking on that link and searching for a dichloromethane MSDS online using this service. It should default to a product details page, but you should be able to find View PDF toward the top right. See if you can identify one potential health hazard for dichloromethane. I hope it doesn't come as a surprise to you that our course comes with a significant number of measurements, and we're going to primarily use SI units, which stands for System International, or however you pronounce the equivalent in French. In this course, we will use each of the top 6 units or derivatives frequently. Each of these base units is described in relationship to a physical constant. This table is actually dated. As recently as 2019, a kilogram mass was defined as the exact mass of one individual physical object stored in France. That's a little bit cumbersome because only a few people have access to that. So since May of 2019, the kilogram is not defined as shown, but is actually defined in relationship to Planck's constant. We will not use candelas at all in this class. As much as we use base units, we also sometimes use derived units, which are related to the SI base units through maths. We don't actually use them differently in most cases, except that if we know a unit has a derived definition, it sometimes helps us to do dimensional analysis. For example, a watt is exactly a joule per second. It's an SI unit for power. But if you want to know how much energy a 100 watt light bulb uses, we can use the fact that 100 watts is 100 joules per second to let us know that if we multiply by time, we'll be able to get energy units of joules. No measurement we can do can ever be exact, except for if we're literally counting things, which means we'll always be estimating a number. The tool we will use will often determine the precision that we can give, but it's also important to convey what we know about precision in the numbers we report. It's kind of like looking at a jar of M&Ms and trying to guess how many are in each jar. Any individual will guess the number of candies in each jar, but most guesses are only going to be accurate to the hundreds unit, and the tens and ones unit will probably be estimated. So we might be fairly certain that there are about 600 M&M minis in the left jar, but we'd have to guess at the tens and ones unit. I might guess 615, but I really only know with any sort of reasonable certainty about the 6 unit, and the 1 and the 5 are both estimated. Significant figures allow us to indicate that right in the number, and the very last significant figure is always the first estimated digit, the one you aren't sure about. So I should actually be reporting for the number in the left jar, not as 615, but if I'm not sure about the tens unit jar, I should say 610 or 620, where the tens unit would be estimated. So significant figures will record every digit that is known fairly certainly, like the hundreds unit in the example before, and then one estimated or uncertain digits, like the tens digit before, so 610 or 620. We can also see that in measurements that we do in the lab. On the graduated cylinder that's shown, the 2 certain digits are 9.6. Look at it and see if you can clearly see that the liquid falls between the 6th line down from 9 and the 7th line down from 9. But since there are no markings between the line indicating 9.6 and the line indicating 9.7, we would be able to estimate but not know for certain the last digit. I think the liquid falls 8/10 of the way down, meaning the measurement I'd give should be 9.68. If you thought it was actually a 9.69, that would also be a reasonable estimate for the same thing. If you thought it was 9.61, you're probably actually thinking about the lines backward. You're forgetting that it's actually going down towards the bottom from 9 to 10. So the higher numbers are closer to the bottom. And so you would sit on a throne of lies and the truth is not in you. An analytical balance is even easier to measure off significant digits. You should record the last digit as the uncertain digit, even if it's 0. If you're getting variation at a higher digit than the last digit, so like if it goes to thousands but you're getting variation in the hundreds, then the scale isn't calibrated properly anymore, and we'd need to re-level it or we'd need to recalibrate it. On a volumetric flask, the uncertainty is actually written on the flask itself. Calibrated autopipettes or micropipettes also have uncertainty indicated by the scale on the micropipettes, but it only is applicable at the very top of their capacity, like in the range of 800 plus microliters for a 1,000 microliter pipette. The lower in the range you go, the more percent variation there is, so it's always best to use the minimum volume pipette that you can. It's also worth noting that if you record a measurement with too few or too many significant figures, it's going to convey false information about how much you know about a measurement. It's a lie then. Don't lie. To avoid this, in high school chemistry or in general chemistry, we told you that scientists mostly use scientific notation. That's actually mostly a lie too, which I suppose I shouldn't have done. Most scientists prefer to use metric prefixes to put something in an appropriate scale instead. This requires that you can use metric prefixes fluently. This is a major objective in both forms of general chemistry here at Trinity. You are likely to encounter the prefixes that are highlighted in red in your normal life, with mega through tera being primarily used if you look at computer speeds or memory, and nano and pico being particularly useful for very small concentrations. You can really just think about each of these prefixes as being the equivalent of a scientific notation number. So if you want to move quickly between picomolar and molar, pico being 10 to the negative 12th, you can just replace the P for pico prefix with 10 to the negative 12th. Easy peasy. Moving the other way just means that you need to get to an appropriate power of 10, so getting to 10 to the negative 12th or 15th, instead of getting to 10 to the negative 10th, and then just swap the letter for the power. We'll do some practice together in class. Suppose I look at a group of people, and I estimate that there are about 20 people. They're a strange group, and I'm not really sure what's brought them together other than an unexplainable urge to congregate in large groups. I didn't count, so the 2 of the 20 is an estimated digit. I really don't know the number to any more precision than that. Now suppose one person left. His name is Gregor Samson, and he never really formed any real connections with the group anyway. Hey, look right where Gregor was. It was pizza. Pizza brought everyone together like a glorious beacon of peace. Anyway, I wouldn't suddenly know that there are exactly 19 people because I didn't know that there are exactly 20 before. I'd still say there are about 20 people. That's because you can't know the value of a calculated number to any more precision than the least precise number you have available. Turns out, it works the same way in all calculations involving significant figures. Whenever you are adding or subtracting numbers, the least precise number controls how precise the result is based on the decimal place of least precision. So one number here is only precise to the 10th digit, so the actual result can only be accurate to the 10th digit as well. For multiplication and division, you are also limited by the least precise number, but now based on the total number of significant figures. Since the 2.57 only has 3 significant figures, the resulting product should also only be reported to 3 significant figures. Of course, if you're paying attention to significant figures, you're often rounding to get the right number of significant figures. Never just stop at the last significant figure. Always round based on the remaining decimals that you won't keep. So as a general rule, 5 or higher is going to make the next digit go up, and the rest will go down. There are more robust rules for rounding well and other calculations that we'll talk about in analytical chemistry. As a quick teaser, this is what you have to look forward to. It's one thing to say we always keep the lowest precision of the numbers we add, but that can be more complicated when the numbers have different prefixes or different powers of 10. Typically for addition, we'll always convert these to the same power, typically the base unit, although we could use a different power of 10, and then only keep up to the least precise value for addition or subtraction. On the top example, the 9.84 at the top right is the 9.84 is only known to the hundredths. And so the answer can also only be known to the hundredths place as well. As indicated before, addition and subtraction are always going to be limited by the value of the last placeholder. So in this example, the placeholder happens to be in the thousandths unit. This is different than multiplication or division, where the lowest number of sig figs are always going to be preserved. In the second of these examples, the 2 sig figs in 3.6 times 10 to the negative 19th limit the significant figures that are reported in the answer. So the 3.6 highlighted in blue is why 1.6 only has 2 sig figs as well, also highlighted in blue. So far, these rules might be review. You probably haven't thought about sig figs for logarithms, which are important for pH calculations. The logarithmic number always has 2 parts. The part before the decimal is called the characteristic, and the part after the decimal is called the mantissa. Only the mantissa is considered significant in logarithmic values, like pH values. As a practice, add together these 4 numbers. I hope that you got 52.0, right? We should have kept the 10th place for significant figures. But now I want you to round every number to the ones digit and then add them together. If you happen to be like me, you probably had a teacher tell you at some point that you should always round 0.5 up to the next number. If you actually do that, you can end up with systematically larger numbers. In this case, it would give you 54 instead of 52 because you'd be adding 12 plus 13 plus 14 plus 15. So instead, we're always going to round to the nearest even number because that will prevent us creating systematically high results. Or even better, we're never going to round until we get to the very end, whenever possible. In both of our courses, water is going to play an outsized role for how we think about nutrient, pollutant, and analyte concentrations and mobility. As we know, the water cycle, or hydrologic cycle, plays a crucial role in getting water onto land, where it's central to all life, and therefore plays an essential role in both the biosphere and the anthrosphere. Rainfall precipitates many atmospheric molecules back to the land and groundwater, and it affects how nutrients are transported in the geosphere. On the analytical side, water is the main solute that we'll be using in lab, and many of the samples that we are most interested in are analyzed as aqueous, that is, water-based solutions. So yeah, water is pretty important. There are many specific fields that study water. Hydrology is a broad field covering all the studies of water, while oceanography is the study of oceans, and limnology is the study of freshwaters. Chicago is actually a really good place to do limnology because we're right next to the largest freshwater system in the world. There are other studies of water too. Dr. S's husband is a fluvial geomorphologist. Fluvial refers specifically to rivers, and geomorphologist refers to a study of how the earth changes. So he studies how river shapes and currents deposit sediments and gradually change the riverbed and bank. It's actually really important for pollutant deposition. Water has a few properties that make it particularly interesting. Most notably, water has incredibly strong hydrogen bonding capabilities for its size, with each oxygen being far more electronegative than hydrogen, allowing it to hydrogen bond very effectively. So the OH bond is really good at hydrogen bonding to begin with. On top of that, each oxygen has two lone pairs, which couple with two other water molecules' hydrogens, allowing water to create complex lattices of hydrogen bonding in liquids and solids, since the lone pairs and hydrogens to bond to them are evenly distributed. Water's strong hydrogen bonding also explains many of its most important properties. For example, its high surface tension, which is essential for plants to wake up water from the soil. You can see in the two bottom images that water molecules must align along the surface to maximize interactions back into the bulk solution. They don't interact very strongly with air. And because they do that, the molecules along the surface are held more tightly, and they're more organized than the average interaction. That's what makes the surface tension. Hydrogen bonding also allows waters to have a high heat capacity. Because the molecules can increase in kinetic energy, they can vibrate and move around a lot without actually fully separating because they're always interchanging hydrogen bonds. And that's really important for regulating the Earth's temperature. It absorbs all sorts of extra energy. It also actually allows water to stratify, that is, form layers in lakes and oceans, which impacts both the currents and the nutrient flow between those layers. Water is also particularly good as a solvent for both polar and weakly ionic molecules, since it can form strong hydrogen bonds with polar molecules, as you can see on the left, or it can solvate ionic molecules, meaning that the water molecules can minimize the impact of charges in solutions by spreading the charge over a larger area. You can see that in the model for sodium and chloride solvation on the right. Each sodium is surrounded by water molecules that make that positive charge spread out further, and the water molecules can do the same thing but oriented in the opposite direction for chloride. In fact, the very properties of water can be an entire class where we turn and worship at the wisdom and providence of our Creator. Water's unusually strong hydrogen bonding underlays every one of the properties listed here, which was drawn from Manahan, except for water's transparency. That's the only one that actually doesn't have anything to do with hydrogen bonding. Since we are in Chicago, we care particularly about the water here in Chicago, which is mostly freshwater and comes almost entirely from precipitation originally. In fact, most of the access to water in the United States is fed by precipitation, pretty much everything but the coasts. And since most water used by humans is freshwater, even coastal areas tend to depend on precipitation. But water isn't distributed evenly across the United States, meaning the types of water concerns in Chicago, like groundwater contamination from heavy industry, may look very different from the types of concerns in Arizona, where the lack of water prevents heavy industry, but groundwater tends to pick up more ground salts as reservoirs are depleted. This will shape both our environmental concerns, but also our analytical methods and challenges. There is some good news here. Since the 1980s, water use has decreased and stabilized. It actually has decreased even more in recent years, as shown in this public domain graph of the United States Geological Survey. But the problem isn't overall use, it's actually that the use has shifted to particular areas. You can see by the large purple swaths in the southwest that much of our population, and therefore water use, has shifted to the continental southwest. And this is our first chance to talk about honesty in data display. The Census Bureau image shows a % change in population, which is generally helpful for seeing if areas are growing or shrinking. However, it's misleading in some cases if we talk about overall changes in population. In some places like California, where a small % change may represent more change overall in the entire population of Montana or Alaska, let alone the changes in some regions of those states. So even though it looks like California might only be growing 2.6 to 9.9% in some areas, that 2.6 to 9.9% probably is larger than the entire population of Alaska, even not considering change. So we care a lot about water, but we also care a lot about what's in water, and depending on what's in it, we may talk about concentrations a lot of different ways, depending on what we're measuring. The top 4 units are all based on mole units, an amount unit, and they're all particularly useful when an analyte, the thing that we're looking at, will undergo a chemical change. For example, it's helpful to know the molar concentration for carbon dioxide that's dissolved in water because it will be in equilibrium with carbonic acid. We always talk about those equilibriums on mole bases. If you look carefully though, you'll see that in the top row, there are 3 different units that all have the same form for the unit, an amount per volume of solution, actually moles per liter. And then there's only one that's different, an amount per mass, moles per kilogram is what we use for molality. So what's the difference between formal, normal, and molar? They matter most with electrolytes, substances that dissolve into ions. Molar should refer to the concentration of actual species. So we're talking about just carbonate or just bicarbonate or just carbonic acid, where formal refers to the concentration of collective species, like all forms of any sort of polybasic anion. Using the same example of carbonate, we talk about carbonate plus bicarbonate, which has 1 more proton, plus carbonic acid, which has 2 more protons. Normal allows us to account for concentrations of an actual species, particularly acids and bases, based on an equivalence factor. For example, if we're talking about the availability of free acid, H2SO4, sulfuric acid, should have 2 times the concentration of H+, as we'd have indicated by the molarity. So the acid is actually twice the normality for H+. The bottom row deals with the types of concentration units that are typically used when we want to control an amount of something. That probably isn't reacting a whole lot. For example, the concentration of ethanol in a beverage is calculated as percent ABV, which is alcohol by volume, a volume percent. The concentration of lead in drinking water might be listed in ppb, or the amount of carbon in steel might be a mass percent. The main focus of our next class on Friday will be working through examples of thinking through these unit conversions. For now, it's worth pointing out that in most cases within water, the things that we might want to measure are parts of dynamic processes that will make molar units the most convenient to work with. However, engineers hate molar units, and most contaminant limits or design specifications will be given in mass percent units, or the very closely related parts per million or parts per billion. This figure shows a number of significant types of reactions that occur in water. And for each of these, if we're truly going to understand how an element, ion, or a molecule exists in solution, we're going to need to use molar units. Even movement within a solution is defined by equilibrium, something that requires molar units. That's a newish concept for students who went the Chem 101 route, but it's a really important concept for understanding how molecules like oxygen move into water from the atmosphere. And because the top layer of water, the epilimnion, epi means above and lim refers to the surface waters like limnology, because that top layer is actually separated from the lower layer, which is called the hypolimnion. Remember, hypo means below, like hypothermia or hypoxia. Since those are separated by a thermocline, a significant temperature gradient, the waters aren't going to mix, and they actually have separate equilibria that govern sediments. We'll again mostly need to use molar units to talk about all of the things that will be in equilibria. And so anytime we have a reaction or equilibria, we're always going to use stoichiometric units, ones that are related to the actual quantities of molecules rather than just the masses. So stoichiometric units are always in mole-based units, so moles or molarity, or even formal or normal. And we can really only do anything useful with them if we have a balanced equation. In natural systems that involve water, which would be the hydrosphere and also most of the geosphere we interact with, and also the biosphere, the amount of freely available hydrogen ion, or H+, or even more accurately, hydronium, H3O+, is a major factor in the behavior of all sorts of systems. However, the concentrations that we might encounter H+ at may be ridiculously high, like 12 molar HCl, or they may be vanishingly small, on the level of 10 femtomolar, which is, by the way, 10 times 10 to the negative 15th, or 10 to the negative 14th, right? That's pH 14. If we use straight concentrations, it would be difficult to compare. So instead, we use the pH scale. The pH of a solution is the negative log of its H+ concentration. This is one equation that you should know. You can also easily go the other way. 10 to the negative pH will give you the H+ concentration. And because pH is a log scale, only the significant figures after the decimal place, the mantissa, are significant in the pH. So a pH of 1.55 only has two significant figures, the 0.55 after the decimal place. We'll actually use the same type of power scale to make other variables more accessible in this class as well. For example, we use pKa, the power of Ka, to describe Ka values, that's acid dissociation constants, on a more reasonable scale. We also use the power function to talk about electrochemical potential, which we'll see later on around Chapter 4 for Manahan and Chapter 9 for Harris, or not, for the Analytical Chemistry 2.1. A few more notes on the tools of the lab. Not all the reagents are of the same quality. A common grade of material is reagent grade. The reagent grade materials are controlled to a given purity and are used for reactions and making solutions in many cases. Some reagents are used to calibrate other reagents. These are known as primary standards and are usually used at a higher degree of purity. These need to be controlled very carefully to make sure that they remain pure, and they are usually needing to be dried when they're measured, which in turn allows for accurate measurements of other solutions. For many types of instrumental analysis, reference standards are used, sometimes with mixtures that will allow for calibrating an instrument at multiple signal locations, like several wavelengths for calibrating with several elements. There are also special purpose reagent grades that have details appropriate for a specific use. For example, HPLC solvents are made to run on a high-performance liquid chromatographer without impurities like water that would change the polarity of the solvent, or impurities that would interfere with the instrument detector for that instrument. And so we'll mostly deal with reagent grade and primary standard grade, but there are examples where you'd come across these reference standards and special purpose reagents. So how do we choose what to use? We're always going to use the smallest bottle available. It's less likely to become contaminated. We're never going to store bottles open. You never know when somebody's going to come by and sneeze and put COVID in that thing. We're going to try to work on clean surfaces and make sure that caps never touch unclean surfaces. Otherwise, you'll have to do what in lab is called a ritual cleansing. Never return excess reagent to the original container. You could contaminate it. And if you can, avoid spatulas in an original container. If you can't, metal spatulas can be reactive, and plastic spatulas are hard to clean. So we generally try to use the ceramic when we're taking things out of the original container. And always, we try to keep a clean lab. A modern analytical balance actually measures force, like weight, not mass. So if you had a chemistry or physics instructor who is really difficult about saying, no, you're going to mass that, not weigh that, they're actually lying and the truth is not in them. It's kind of our theme for the day. They actually even more specifically measure how much current is needed to apply an appropriate force to keep the balance from moving out of a magnetic field. However, we calibrate based on mass standards. So you can use mass or weigh, and both of those work. Because the current required to preserve the sample location is dependent on any drag on the balance, it's really important that the balance be clean. So clean up any spills immediately. The required current can also drift, so it's important to re-zero or tear before measurements. If you've ever teared an instrument and then walked away for a while, you'll notice that it doesn't read zero anymore when you come back. There are several ways that you can make an accurate measurement of the solid. You may choose to tear with a container already on the instrument so that only the mass that's added is measured. This really only works if you're going to take the measurement right away. Otherwise, someone else might change the tear or the instrument may drift. And if you don't notice, your measurement will be wrong. It's better to measure an empty container and then measure that full container and then find the difference to figure out how much you put in it. You also can take the mass of the container you're measuring from, so like whatever bottle you're pouring from, before and after you remove the sample. This is called weighing by difference, and it only works if you don't spill. It's really important to make sure that you avoid contamination by fingerprints as well if you're dealing with very low mass measurements. And even air currents can change things, which is why our scales have a box around them. Many of the reagents we use take up water from the air. We call those reagents hygroscopic. If a reagent takes up water from the air, the mass will no longer be accurate unless we dry it. So we'll often use an oven to evaporate water and then a drying container called a desiccator to cool it down gently. When we measure volume, we have a number of tools of varying accuracy. Just like we talked about in lab, volumetric flasks are usually best for fixed volumes, like if you know you have to bring a solution up to 100 milliliters or 500 milliliters. Pipettes and calibrated pipettes tend to be the most accurate for variable volumes. Like if you needed exactly 1.7, you probably don't have a volumetric flask that can do that. The micropipettes, like those shown in the top right, are fairly accurate if they're recently calibrated and they're near the top of their volume range. But as they go further down in their volume range, become less accurate. And syringes are pretty effective for very small volumes. Also, like we talked about in lab, the volume of a material is not fixed. If you're using volume for a primary measurement, it actually really matters what the temperature is. That's why it's important to use a temperature-based density to convert between volume and mass, just like we did in lab. And since we often dry materials in the oven, we also need to let it cool completely for the mass to be accurate, around 20 minutes. If you take it out sooner, the air on the scale warms up and there's less mass in that box, and a systematic error occurs where we'll actually measure less mass than is there. And finally, a note on cleaning. When we clean, we need to remove both organic and inorganic contaminants. Organic contaminants require detergent to actually dissolve them, because like dissolves like, and the detergent has a long nonpolar chain. Inorganic contaminants require DI water. On some occasions, salts with limited solubility are removed by nitric acid. In general, we should start by washing with soapy water. Then we rinse with tap water to get all that soap off, and we rinse with DI water to get rid of any of the remaining salts from the tap water. If you absolutely need no ions in your solution, you can follow up with a rinse with type 1 ultra pure water, which is really only necessary when we're doing trace or ultra trace analysis. If you need to dry that glassware quickly, air and paper towel both deposit particles onto the glassware. That's generally not a good idea. So instead, we'll dry with a flame, like light that thing on fire, or we'll dry it in the oven. In rare cases, organic solvents may be used and the process repeated. This is actually fairly common in organic, which is why often we'll rinse with acetone first, but it rarely happens here.